Hi, everyone. I hope everyone's doing good. My name is Sheldon Fernandes, and I'm with Lucid. We are a computer vision company, and we work a lot with cameras, stereo cameras, and we do all that it takes to make the stereo camera into a 3D camera. And since most of you were here for the previous presentation, we focus on the first type of stereo systems out there. That is a baseline divided stereo system with 2 cameras. And as I told you, we do what it takes to make this into a real 3D camera. And today, I'll be speaking to you about what I think is one of the most important steps in making this system into a 3D system, and that's the process of calibration. And I'll be spending a lot of time on calibration in general, but I'll also go over a few other things that make up a stereo camera. So we'll start off with understanding why calibration is so important in constructing a camera. Then we'll go on to see what the overall flowchart is. We'll see when calibration happens, how long it takes, what all the steps involved. We'll look at some math, the parameters that make calibration do what it does. And we'll look at how we get this data in a very controlled environment. That's factory calibration. We'll also look at calibration in the real world as to how we can make small tweaks to calibration just in case it goes bad. And finally, we'll end with how this data is so valuable now that it can be used for more critical tasks in the real world. So I'd like to show you in the beginning what bad calibration looks like. What you see over here is just my keyboard, and it's an overlaid left and right frame from a stereo camera. And if you look very closely over here, you'll see that there's a lot of distortion in the left and the right frames, but also there's some amount of misalignment in the left and right frames. And if you look at this picture on a real 3D screen or one of those polarized screens, you'll see that things don't quite add up. It might hurt your brain a little bit, your eyes might water. It might fix all those problems in your brain, but it's a really uncomfortable experience. And that's exactly what bad calibration is defined as, a really uncomfortable experience to view 3D. And our goal is to alleviate all these problems by doing the calibration process. So calibration is one of these things that if done really, really well, it goes completely unnoticed. Everything looks great. You see a 3D screen just like you're watching 3D right now with your eyes. And it looks great. But if done really bad, it's going to hurt you so bad that you'll probably give up 3D, having 3D experiences. I know a lot of people who say, I'm not going to use 3D anymore. I just find it really uncomfortable to watch. It hurts my eyes so much. And that's exactly the problem that we're trying to solve. And we're pushing the bounds by making the system extremely smart, as we'll see in this presentation. And I'll be honest, calibration is not just a process for stereo cameras. It's a process every camera goes through. But its effects are really critical and are more noticeable in a stereo system. And that's what all this presentation is about. So this is a complete overview of constructing a 3D camera in general. And it's got 3 different sections. And the first one is the one I'll be focusing on the most. That's the calibration process. On the second row, what you see is how this calibration data gets used in real time. And finally, the third row is about using this valuable data at the end of it to do advanced processing and more important tasks with this data. So let's start with understanding what parameters actually make calibration do what it does. And I'd like to do this with an example, obviously. Let's first look at intrinsic parameters. These parameters are parameters that relate to one camera in specific. That is, it could be done for any cell phone camera out there. If it's a stereo camera, intrinsic happens for the left and the right. And this picture over here on your left-hand side is of that of an uncalibrated frame. And if you look closely, you'll see straight lines do not add up. They are obviously not straight. You also see, if you look closely, that the lens is not exactly in the center of the sensor. And there's a lot of distortion, and it's not comfortable for viewing. But then on the right-hand side, you see the same image that looks perfectly like how you would see it with your own eyes. Now, going from left to right, we obviously have to do some amount of warping, some amount of math in going from left to right. And there's many unknowns. So these unknowns are defined right here. There's amount of distortion on the tangent. There's some amount of distortion along the radius. And that's what we define by our distortion coefficients. We also have a few more unknowns like the camera centers and the focal lengths of the lenses. And in knowing all this information, can we go from the left to right, as we call an undistorted frame. And monocalibration, as I said, happens for both left and right, and it's very critical for the next step that I'll be talking to you about, that's stereo calibration. These are the parameters that make stereo calibration do what it does, and they are mainly divided into rotation matrices and translation vectors. Rotation matrices basically tell you the information as to how my left sensor is rotated with respect to my right. And it gives you, we'll look at rotation matrices later in this presentation and how it's important. But essentially, what we need to define a stereo pair is rotation and translation. And in knowing all of these values, can we define a stereo camera? So finally, as we saw in these two slides, we have intrinsic and extrinsic. And in knowing all these values, the focal length, the camera centers, distortion coefficients, and all of these parameters you see, can we form a signature that defines a stereo pair of cameras? So now, if by some means we can get all of these values, we know everything that we need to know about these stereo cameras. And if we have everything we know, can we rectify data and alleviate all the problems that's caused by bad calibration? So this is the process of calibration that happens in a very, very controlled environment. You guys must have seen chessboard targets, very common out there. The only difference over here is that these chessboard targets are RGB targets, red, blue, and green, and they are mutually perpendicular to each other. And it's rotated on this one platform, little off-center, to get as many views as possible. What we're trying to do over here is gather as much data from our lenses as we can, and use this data to compute all of those parameters that we spoke about earlier. So this is a case in which, I'm just talking about one chessboard target over here. In the first step, we gathered data, and as you see, this data looks, there's no alignment between the data, and also there's a lot of distortion within the frame. And our first step over here is to undistort this, that is, get all our intrinsic parameters, also called as monocalibration, and undistort the frame. But again, as you see over here, the frames are not lined up. And that's when we move to our next step of stereo calibration, where we make sure that everything is rectified, everything is aligned. Now, at the end of this, everything looks great, but we need some metric to understand as to how good our calibration is. And that's just the root mean square error, also known as the reprojection error. And what we do is we compute calibration multiple times by changing the complexity level of the model, of the distortion coefficients, use different subset of images. Also, for variable baseline cameras, change that. Finally, to get a reprojection error of less than 1 pixel. And that's when we say, OK, if we have sub-pixel accuracy in reprojection, we are really good. For those of you who are not familiar with the concept of reprojection, what it means is basically the difference between the actual output and the desired output. In the chessboard system, we know exactly what the actual output should be because we've defined the dimensions of the chessboard. We've said what it should look like. And finally, we know what we get from the rectified output. Just the mean difference between all of these points gives us a reprojection error. So after this calibration process, everything is great. We know all the intrinsic, all the extrinsic. We know everything that defines the camera system. But there's one small problem over here. Say, for example, using these cameras in a normal cell phone. Unfortunately, we are not great with cell phones as human beings. We drop our cell phone all the time. A lot of us sit on our cell phones. And as any electronic device, there's some amount of heating and cooling that happens inside. There's a lot of changes that can occur in electronic circuits. And all of this results in one small problem of modification of extrinsic parameters. So right after stereo calibration in the factory, as we saw before, we see that rectification is perfect. And if you match feature points from the left and right side, they are all horizontal, all zero slope, and everything looks perfect. And we asked ourselves the question. We know exactly what the raw output is. At the same time, we know what the rectified output is because of calibration. And we have this one unknown in between that we've solved using basic calibration in the factory. But is there something else that we can do to identify what goes in that box in between that creates this perfectly rectified output? And just as every engineer out there, we thought, let's break this problem into its really basic bare bone and solve that first. And we noticed that mainly what changes in a stereo system due to rough use of, or due to heating and cooling, is rotation matrices. And a rotation basically can be broken down into its three basic components. That's yaw, pitch, and roll. That's defined in this diagram, but I'll just like to demonstrate that to you. Basically, pitch would be any rotation in the up-down axis, yaw in the right-left axis, and roll in the axis along pointing outward. So basically, if we know all of these parameters, we can get a rotation matrix. So we asked ourselves, can we compute these values just by looking at the raw data and the rectified data? And moving a little outside of this technical system and thinking about biology, that's exactly what our eyes do. I'm not a great biologist or anything, and this is just an analogy over here. But as we grow up with time, our eyes change, but we don't have problems seeing 3D. For example, growing up, we don't have problems understanding how far objects are. Our eyes, our brain always learns things in real time. And that's exactly what our inspiration was behind this project. So we asked ourselves, can we somehow train a model using good features to give the same yaw, pitch, and roll as that of factory calibration? And that was the basic project that we came up with at Lucid. So this is a very high-level block diagram of what we thought we should do. So we said, OK, let's get some features that are good, because we don't want to train our model using really bad features. So we said, what kind of features are good? We can get normal features, but we can also get linear features, because they store a lot more data with respect to angles as compared to just point features. So we said, OK, let's get features from these images, and somehow let's train a model. And let's try to minimize the error between the model's yaw, pitch, and roll, and what we get in factory calibration. And then we check if our calibration is still good. We check if all the slopes are nearly 0. And if all of that is good, we say, OK, we can keep doing this process and make our model really strong. And down the line, when our calibration worsens, our straight lines are not straight anymore, roughly 2 years, don't quote me on that. Now we have this very rich resource. We have a trained network that can look at the raw input and can predict the values of yaw, pitch, and roll. So we have this really good resource with us, and we say, OK, now we have this resource that we can use, and we can use this to compute the yaw, pitch, and roll. That is, we can use this to compute the rotation matrix. And finally, encode this data to make this data to get a newer calibration file, to get an updated calibration file. So our goal, as I said before, at the end of the day is to make a camera, make a stereo pair of cameras there as close to the human eye that is completely self-calibrating. So this is what we've been working on at Lucid, and this data is not so much of use until it can be used in real time for any more processing. So what you see in the middle section over here is rendering, and I'd like to take some time to talk about how this data can be used in real time. Over here, we have 3 examples. On the left-hand side, it's just a very sleepy version of me, and which is perfectly rectified. In the middle is an anaglyph version of me, and if you had one of those anaglyphic glasses, you'd actually see me in 3D. And on the right side, we have something I'd like to take a longer time to talk about. That's zero disparity correction. What happens when we look at a close object? For example, if you look at your finger that's really close to you, what happens is your eyes kind of bend inward so as to have a zero disparity plane on your finger. That means your finger is completely in focus. All points behind your finger are now where rays cross over. That is, has negative disparity. And all points between the finger and your eye have positive disparity. And that's exactly what we can do with perfectly rectified data. We can get a good depth map. And as you can see, what I've tried to do with my Starbucks cup is have a zero disparity plane over there. And this is what generates perfect 3D in real time. And finally, now we have a lot of information with us. We have this perfectly zero disparity corrected frame. We have perfectly rectified frame, even if it's not zero disparity corrected. And now we have this data that's so valuable that can be used for a lot of advanced processing. I have a few examples up on the screen, but these are very limited examples. Anything our mind can think, any problem that's currently solved using different kind of technology out there can potentially be solved using a stereo pair of cameras. And this is basically what we've been focusing on at Lucid. So in conclusion, I'd like to take a look at this presentation backward, not where we started, but where we ended. We ended with saying we want all of this. We want to do a lot with stereo data. We just don't want to take pictures and save it onto our cell phones. Now for this to happen, we need to have rendering in real time, which as you saw is possible. And for rendering to happen in real time, we need perfect calibration. And we need a camera that's always has a really good calibration file on it. And that's exactly why I started this presentation by telling you that calibration is key to making a perfect stereo camera. So thank you for listening to me, and this was really great. It's me and Joe in the audience from Lucid, so if you guys have any questions, please feel free to stop us and talk to us at any point in time. Thank you.
Questions?
What do you know about the uptake of stereo cameras on smartphones? I'm familiar with only a few models that are quite old that have stereo cameras.
Yeah.
I've been a stereo photographer for years with a Fuji WM3.
Oh yeah, that's the nice one.
I love, and I would love to have stereo camera in my phone.
And that's what we'd like to give you. So we've been working on a stereo camera. And this is definitely public information. We've been working on the red hydrogen camera. It has a stereo pair on the back and the front, and it can create stereo in real time. It's just perfect, like a click and go. And it has everything that I spoke to you about, along with zero disparity correction. So the phone's not out yet, but very shortly, roughly in the time frame of August, September is what I last heard. And I'm sure you love the camera. You should definitely check it out. I think the launch is going to be real soon.
Does this help calibrate cameras from, like, if you put multiple cameras?
Yeah, so currently we work with 3 different types of cameras out there. We started off with working on a consumer camera that had fisheye lenses, and that was the picture you saw up there. We also worked on a cell phone camera, front and back, with different baselines, 13 and 7 millimeters. And we also are working on a bigger camera with a variable baseline. So we've tested the system out on various cameras out there. And coming back to your question, this system can be extended to be used for multiple cameras as well. It's not used exactly in that context right now, but it's definitely not something that's built only for one specific purpose.